slightly differently today because of the in-depth detail of the different mechanisms we're going to do. However, I do an annotated version where I actually write the structures on the video, so start looking for those as well. Okay, so in this chapter, we're going to look at the major mechanism we're going to use for almost all the reactions until we start doing reductions at the end is what we call electrophilic aromatic substitution. Okay, what that means is that an electrophile is going to come in and substitute a hydrogen on the benzene ring, and that way we can generate this new reaction, this new substituent on the benzene ring. So in all cases, we are going to be displacing a hydrogen, okay? In all of these cases, we lose that hydrogen. It is a very acidic hydrogen because it wants to get back to aromaticity. So it's going to lose that hydrogen, keep those electrons, and regain its aromaticity. That's the driving force on this on this mechanism. So we want to see that hydrogen leave as our last step. Okay, and this is probably 90% of benzene reactivity is this reaction. So if you learn this one mechanism, all you have to do is look for your electrophile. Okay, so in this case here, we're going to always have our benzene ring. We're going to always have our electrophile. Now, our electrophile here is typically something that we have a complex between something that has a nonpolar bond and something else to generate a polarized bond. We need to generate a polarized bond to get something that's positive or partially positive to get it to react with the electrons in the benzene ring. And we're going to see that time and time again. The first step in all these reactions is to generate that electrophilic reagent, okay? The second step in the mechanism we're going to see is those electrons from the benzene are going to reach out and grab that electrophile and create a new sigma bond. And we're going to have a loss of that sp3 hybridization into an sp4 hybridized carbon. And then by losing that hydrogen as a positive and taking those electrons back, regaining our sp2 hybridization, we will regain our aromaticity. And again, that is the final step, is that loss of a positive hydrogen on our system. Okay, so let's look at that in a little more detail. Okay, if we look at the energy diagram, we have our benzene is really stable. So we're actually starting fairly low in this free energy state right here. And then as the benzene gets close to our electrophile, what happens is the electrons kind of start to reach out and grab at that electrophile, and we generate this transition state here. Okay, notice that we only have a partial bond to that electrophile. Okay, and that electrophile at least has a partial positive charge or a full positive charge. Okay, now once we pass this transition state here, we generate our intermediate. Our intermediate is always this aryl cation that is delocalized around as many carbons as possible. Okay, and sometimes substituents, which we'll see in a little bit, but it has changed the hybridization of this carbon from sp3 to sp2, and we no longer are in conjugation here. Now, at this point, something in the solution, and it's typically part of that electrophilic reagent, will act as a base. And it will pull that hydrogen away. And when it does, the electrons that were bonding that hydrogen to that sp3 hybridized carbon go back into the ring, and we regain aromaticity, and we lose our hydrogen is typically bound to whatever was acting as the base in our second transition state here. And then at the end of the reaction, we end up with our new compound, which is typically more stable than the original hydrogen on the aromatic ring. Okay, so these three steps are going, this, formation of the electrophile, the formation of this intermediate here, and notice that we have these partial positive charges. Those are going to come in handy when we talk about direction and where things are going to react. And then we end up generating our hydrogen and our substituted material at the end. Okay, so we're going to look for each one of those steps in each of the reactions we're going to be doing. Okay, so that is too far. There we go. All right, so let's go to our first and simplest, which is halogenation. We're going to take our benzene ring and add a chlorine or a bromine to it. Okay. Now, the bond between two chlorines is nonpolar because they both have the same electronegativity, the same for bromine. So we want to use something to polarize that bond. And to polarize that bond, we're going to use a Lewis acid catalyst. Okay. In the case of chlorine, we want to use ferric chloride, or FeCl3. In the case of bromine, we want to use ferric bromide, because if you have a ferric chloride and bromine into it, you can actually scramble those halogens and you'll end up with some bromine and some chlorine in there. So we always use the same halogen on the Lewis acid as we are trying to put on the ring. Okay, and if, as we showed before, when we were looking at the stability of arenes, we saw that if you just added bromine to benzene and just kind of cooked it along, nothing happens. That benzene is too stable, it doesn't do that addition reaction, and it doesn't do a substitution reaction because the bond isn't polarized here. So we're going to weaken that bond and make it a really good polar compound to make it react as an electrophile. Okay, so the two common reactions we'll see here are just benzene going to chlorobenzene and benzene going to bromobenzene. So if we look at the mechanism, again, the first step in all these is the generation of the electrophile. We have our bromine as a nonpolar compound here, acting as a Lewis base. It has electrons to donate, okay? So it's acting as a Lewis base, and our ferric bromide is acting as a Lewis acid, is accepting those electrons, okay? When it does that, it creates this intermediate here, right here. So this is our Lewis acid, Lewis base complex. And this Lewis acid, Lewis base complex now, notice, has a very polarized bond. We have a positive charge on bromine and a negative charge on the ion compounds, okay? So this is the positive source of where we have that positive bromine gives us a chance for it to interact with electrons from the benzene. So the next step in the reaction here is the electrons from the benzene ring reach out and grab at the bromine right here. When it does that, the bromine that has the positive charge takes the electrons that it's bound to and pulls it back in, and then we end up with a charged complex of FeBr4-, okay? Now, the other thing we get from that is this addition product, or this carbocation and our new sigma bond to bromine, okay? Now, we have a carbocation that's next to a double bond. So we can delocalize that positive charge and stabilize it to some extent. And so when we use resonance to delocalize that charge, we can see that the electrons will kick in over here, and so our positive charge moves to here. We can do it again, and our positive charge will move to here. So this will continuously move around the ring until we have an event happen. And the next event that happens is we have to have a Lewis base, or something that has electrons to donate, reach out and start grabbing at that hydrogen, okay? Remember, because of this aromaticity, because of the delocalization, this hydrogen wants to leave and leave those electrons to re-aromatize the ring, okay? So in the third step here, we have this FeBr4- complex having the electrons it can donate to the hydrogen. So it is our Lewis base, and it's reaching out and grabbing that hydrogen. The electrons that were bonding that hydrogen to the benzene ring now go back in. Now we have 3 pairs of electrons in that ring. Therefore, we now re-aromatize the ring, okay? And when we do that, it spits out a complex with HBr, and then we regenerate our Lewis acid catalyst. We've generated HBr. The H came from the benzene, the Br came from the bromine, and we have our new brominated species, okay? So if we look at the whole thing together stepwise, we generate our electrophile first, okay? Our benzene then interacts with that electrophile to generate a carbocation and an sp3 hybridized center. We lose a hydrogen to regenerate our sp2 hybridized center and re-aromatize the ring, okay? So the idea here is that, you know, we have to make that Lewis acid, Lewis base complex to make the electrophile. Once we make the electrophile, the benzene does all the work, and then we have to have that Lewis base come in and pull that hydrogen off to re-aromatize, okay? So the mechanism works exactly the same for chlorine, except we've replaced all those bromines up in the top first step with chlorides. The same steps happen, and we end up generating our chlorobenzene. However, this does not work with iodine because iodine is too big and fluffy and non-reactive. And it does not work with fluorine because fluorine is way too reactive and will over-fluorinate the ring. So this specifically works with bromine and chlorine. Okay. So the next reaction I want to talk about is nitration. Okay. Now in nitration, what we're going to do is we're going to convert, whoa, where'd it go? There it is, nitration. Okay, so we're going to take that hydrogen off of that benzene ring and we're going to add a nitro group, okay? So this is a really good way to get to aniline, which is the amino group on benzene. Okay, you cannot use an amine to attack it directly because you're never going to form a positive charge on an amine, but you can on a nitro group. So we can't do electrophilic aromatic substitution with an amine, but we can do it with a nitro group. So whenever we convert a benzene to an aniline or having an amine functionality, we typically nitrate first and then do a second step, a reduction. And so there's a couple different reductions we're going to learn as the second step after some kind of nucleophilic, electrophilic aromatic substitution. But common ones are just tin metal and acid, or hydrogenation works as well. And that'll convert our nitro group down to the amine. Okay, but the first thing we want to do is put that nitro group on there. Okay, so just like before, the first thing we need to do is we need to create our electrophile. And so to create our electrophile with the nitration reaction, we take nitric acid and another strong acid, sulfuric acid. And we use sulfuric acid to protonate the OH on nitric acid to make this complex where we have a water as a leaving group and a charged nitronium species here, okay? So, and then we also generate this right here. This is hydrogen bisulfate. So it is now our Lewis base. We're going to use that at the end, so keep track of that. Okay, so once we form that, we can lose water. We're going to generate water plus the nitronium ion. Notice there's a true formal positive charge on the nitrogen in the nitronium ion. Okay, so this is now our electrophile that we just generated. Okay, so once we have our electrophile generated, we can have just like before, the electrons from the benzene ring reach out and grab onto that nitrogen. Notice whenever I do this mechanism, I always put the hydrogen here. When you draw this mechanism, always draw the hydrogen there to make sure you don't forget it's there and you're not, because that's the hydrogen that's going to leave at the end. So always add that. So once we add our nitronium ion to there, we generate our carbocation, which of course is stabilized across as many carbons as possible, giving our uranium ion here, our cation. And then of course we have incoming as our last step, something comes in and acts as our Lewis base. In this case, we can use water, or we can use the bisulfate ion here as our base. It'll deprotonate the uranium ion and generate our re-aromatized nitro compound here, plus our protonated water or sulfuric acid species. Okay, so again, all three steps are the same. The only difference is the generation of a different positively charged species that reacts with the benzene. Okay, So let's go and instead of a nitro group now, let's add a sulfate group, okay? And I'll show you that the reaction mechanism, again, is exactly the same. In the case of adding a sulfuric group or a sulfonic acid group to the system, what we do is we typically take SO3, which is a gas, and have a saturated solution of SO3 in sulfuric acid, and that will sulfonate the compound, okay? Now, unlike the addition of chlorine and bromine and nitro, this reaction is actually reversible if we have the addition of water. If we did this in a dilute reaction, we can actually remove this SO3 from the system, and we can then actually use this as a group where we can block a section with the sulfonic acid and then remove it again at the end. So this is the only one of these substitution reactions that's reversible, but keep that in mind. But let's look at the mechanism directly, okay? So in the case of that, we have SO3 interacting with sulfuric acid. It is protonated by the sulfuric acid to generate this species here, which is our true electrophile. Notice we have a positive charge on sulfur. And yes, if you count the number of electrons around that sulfur, we do have 10 electrons around that sulfur. It's in a group 3, so it can have more than an octet. Okay, so we're going to generate that as our electrophile, and this becomes our Lewis base that we'll need to remove that proton at the end. Okay, so now we have attack by the electrons of the benzene ring out to that positive charge, changing our hybridization again, and then having attack by our base to deprotonate our iridium ion here and regenerating our aromaticity, generating our sulfuric acid catalyst back again. Again, we're going to use this tool a little bit toward the end of the chapter as a possibility of blocking a section and then be able to regenerate that proton from the compound. All right, so we've shown you that the same mechanism works for 3 or 4 different electrophiles: the chlorine, the bromine, the nitro, and the sulfate. Okay, now the next 2 reactions fall under a set called Friedel-Crafts reactions. And in both of these cases, we're going to create a carbocation, or at least a positive charge on carbon, and we're going to create a carbon-carbon bond. Okay, so I want to make it very clear that in the next 2 sets, we're making carbon-carbon bonds, and so that's a little different than the first 4 we did. Okay, so in the case of the Friedel-Crafts alkylation, that means we're adding an alkyl group. Okay, so this is going to be a CH2, CH3, something like that. Okay, so this is the alkylation. Okay, and we do that by starting with an alkyl halide and something to generate that positive charge. And in the case of this, we're going to use a different Lewis acid. For the Friedel-Crafts alkylation and acylation, we're going to use aluminum chloride as our Lewis acid catalyst. Okay, so we would typically take benzene right here, take our alkyl halide, our aluminum chloride, and just heat this up, and it will generate a new carbon-carbon bond plus HCl, plus we regain our Lewis acid aluminum chloride. Okay, so in the case of alkylation, we only need a catalytic amount of aluminum chloride. Okay, that is not true for acylation. Okay, so in the case of something simple like this ethyl chloride here, we can generate our charged species, our carbocation species, and then add that chain to the system here. Okay, so this is just adding an ethyl group to that, going from benzene to ethyl benzene. If we use a tertiary alkyl halide, we'll end up with a tertiary carbon here, and so this would be T-butyl benzene, T-butyl, or T-butyl phenyl let's see, forgot the name. Anyway, it's this T-butyl group is hooked onto the benzene there, so that is the T-butyl benzene. Okay, so let's again see how we generate that electrophile here. So when we generate that electrophile, we are going to be doing the exact same thing, creating that Lewis acid base complex to get a polarized bond between the carbon and the halogen, in this case, a chlorine right here. So if we see this in primary and secondaries particularly, I'm sorry, tertiaries and secondaries in particular, they form very quickly and form this carbocation. Secondary carbocations and tertiary carbocations are more stable. In this case, we form that tertiary carbocation, which is then the reactive species. The benzene reaches out, grabs it, and pulls it in, and then our aluminum chloride complex acts as our Lewis base to deprotonate the intermediate. Okay, so in the case of something like a tertiary alkyl halide, you will always get a bond where that halogen was. Okay, so if you had the T-butyl chloride, you will always get a T-butyl group. If you have a secondary alkyl halide, you have to worry about carbocation rearrangements. Remember, if it can rearrange to a tertiary carbocation, it will rearrange to a tertiary carbocation. So if we look at this secondary halide here, notice that we started with it on this bond here, on this carbon here. But once you form that carbocation here, it could do a 1,2 hydride shift and form the carbocation over here as a tertiary carbocation. That would be the reactive species, and therefore we actually get that tertiary alkyl chain on that benzene ring. Okay, so because we're generating a carbocation, we have to worry about carbocation rearrangements. Okay, so let's look at the mechanism here. And it's just like before. We have our reaction with our polarized carbon-chlorine bond to generate our initial complex right here. And then that complex can break apart, giving us aluminum chloride 4 minus as our Lewis base, and our carbocation. Our carbocation then has an opportunity to do two things. If it's a tertiary carbocation, it's ready. It's going to react with the benzene ring and nothing else is going to happen. If it's a secondary carbocation and it can do a 1,2 hydride shift, it will. Okay. Some secondary carbocations do not rearrange because there is nothing more stable available to it. But if it can rearrange, it will. And in this case, it rearranges by a 1,2 hydride shift. And then we have attack by the benzene at the most stable carbocation formed. And then our aluminum chloride 4 minus comes in as our Lewis base, pulls the proton off, and then re-aromatizes the ring, regenerates our our aluminum chloride, and liberates one equivalent of the acid halide, in this case, HCl. Okay, so again, every step that we saw is the same in the previous reactions, except for the possibility of a carbocation rearrangement. Okay, so now, if we want to generate something that uses a primary alkyl halide, we have to take a couple things into account. First of all, we can do it if there's no possibility for that primary carbocation to rearrange. So for example, in the case of this ethyl chloride, or if we had methyl chloride, we can generate that primary carbocation and it will not rearrange, and therefore we can get the straight chain alkane, like an ethyl benzene or a methyl benzene, or as the common name would say, toluene, directly from that alkyl halide. Okay. However, if you have a primary alkyl halide and it can rearrange to form a secondary carbocation through either a 1,2 hydride shift or a 1,2 methyl shift, it will. And so for things such as methyl and ethyl, you can make them directly. To make the propyl, you cannot make the propyl using a primary alkyl halide because it's going to rearrange and give you the isopropyl carbocation here, and that isopropyl carbocation is going to give you the isopropyl group on the benzene ring. Not your straight chain propyl, but the secondary carbocation version, which is the isopropyl derivative. Okay, so it's hard to get long straight chains through this Friedel-Crafts alkylation, but we have a workaround, so just wait. Okay, so 4 things to remember about the Friedel-Crafts alkylation reactions is that carbocations will rearrange. Okay, so in the case of this example here, we're using bromobutane right here. And if you wanted to get the straight chain bromobutane from this reagent, it is only going to be your minor product, because as soon as you form that primary carbocation, it's going to rearrange to give us our secondary carbocation, and we'll actually end up with this second butyl as our major product. Okay, so first rule is carbocations rearrange. Okay, so propyl or longer is always going to rearrange to give you some kind of secondary or tertiary substrate. Okay. Now, the second thing to know is that it works with sp3 carbons only. Okay, so which means if you had the vinyl halide or an aryl halide, these do not undergo the formation of the carbocation, so neither of these substrates can be used to attack benzene. So this means you cannot make styrene or vinyl benzene directly from a vinyl halide and benzene, and you cannot make 2 benzene rings stuck together using the Friedel-Crafts reaction. You have to use a different reaction for that. Okay, so in both cases, these are sp2 hybridized carbons, and sp2 hybridized carbons do not work in this system. And it all goes down to the idea that that vinyl carbocation is the least stable carbocation, and it's very difficult to form. So we do not see this reaction happen. Okay. All right, so one thing you also need to know is, as soon as you alkylate a benzene ring, it becomes even more reactive to alkylation. Okay, so what this means is that if you only want to monosubstitute your benzene, you actually have to use your alkyl halide as your limiting reagent. In fact, a lot of times, if you want to do this reaction, you actually use benzene as the solvent, and you just add as much of the alkyl halide as you want to make of your product, and then you just separate them at the end. Okay. Now, notice here, I have a different Lewis acid here. I don't have aluminum chloride. There are several other strong Lewis acids that will work, including BF3, which is in here, or HF. HF is sometimes a strong enough Lewis acid to generate that carbocation and get that reaction to work. So aluminum chloride is the #1 used. However, BF3 or HF can also both be used as our Lewis acid catalyst. Okay. Now, what if you don't have an alkyl halide? Can you still do a Friedel-Crafts alkylation? And the answer is yes. If you have some substrate that will either add something to it, for example, in the case of, here we have an alkene. Just like when we start to think about an acid hydrolysis of an alkene to generate an alcohol, the intermediate on that is a carbocation. So if we had an alkene, we can add an acid to it to generate that carbocation. Then that carbocation can react in the Friedel-Crafts alkylation reaction. Okay, the same can happen for water. We don't have to convert it from the alcohol to the alkyl halide using thionyl chloride or phosphorus pentachloride. We can actually use the acidity of the Lewis acid to protonate the alcohol and have it leave as a leaving group and generate our carbocation. Okay, so this is an unusual way to do a Friedel-Crafts reaction. However, notice that all we're doing is creating that carbocation. We're not changing the mechanism, we're not changing it, we're just changing the way we create the carbocation. So any way you can create a carbocation, you can react it with benzene. Okay, so that's kind of closing all of this together with the alkylations. Okay, so remember those 4 rules that you can only make primary straight chains if they're short because of rearrangements. They can rearrange, they will. For longer ones, you're always going to get to the secondary or tertiary carbocation. You can use several different Lewis bases available to you, and because once you alkylate it, it actually becomes more reactive, you typically want to use benzene in excess and your alkyl halide as your limiting reagent. Okay, all right, so let's move on to the other Friedel-Crafts reaction, the Friedel-Crafts acylation. Okay, so the big feature difference about the acylation and the alkylation is we're going to be adding a carbonyl compound. We're making a ketone. Okay, in the alkylation, we were making a carbon-carbon bond and we had a hydrocarbon. In the acylation, we always make a ketone. Okay, so that's the key here. If you see a ketone in the product, it's an acylation. Okay, so anytime you add a ketone or to the benzene ring, we call that the acyl substitution or an acyl group on the benzene ring. Okay, so that can be an aliphatic group, or it can be a benzoyl group. Okay, so if you can think about it, this is a derivative of acetic acid, so it's an acetyl group, or this would be a derivative of benzoic acid, so it's the benzoyl group. Okay, in both cases, we start with some carbonyl compound, and it's either an acid chloride right here or an acid anhydride. Okay, the reason we use these is these have the best leaving groups and it's easiest to generate our carbocation in them. In both cases, just like in the alkylation, we use aluminum chloride is primarily used as our Lewis acid. Okay, and in both cases, we end up quenching them at the end, typically with water, to generate our acyl group or our new aromatic ketone. Okay, so again, the mechanism is exactly the same. The first thing we have to do is we have to create our electrophile. And in this case, we make the acylium ion right here. So in the case of an acid chloride, it will react with our Lewis acid catalyst and it will create our Lewis base, aluminum chloride 4 minus, and our acylium cation. So now we have a full positive charge on that carbon. Okay, now these do not rearrange. We formed a carbocation with a polarized carbon-oxygen bond here, so it does not move. Okay, so we don't have to worry about rearrangement. It's just wherever that acyl group was is the part that's going to bond to benzene. Okay, so that's a bonus for the Friedel-Crafts acylation here. So again, the next step is attack by the electrons of the benzene ring to the cation right here. We'll generate our intermediate charge species here, and our Lewis base is going to come and take away our last proton to re-aromatize it. We'll generate our aromatic ketone, plus we'll end up with, in this case, HCl, plus we'll regenerate aluminum chloride. Okay, now I said that in Friedel-Crafts alkylations, you only need a catalytic amount of aluminum chloride. Okay, in acylations, this isn't true. We actually have to use excess acyl chloride. The reason is that because it's a Lewis base, the new carbonyl ketone can react as a Lewis base to form a complex. Okay, so if we look at the bottom of the page here, we see that that new carbonyl has electrons to donate. It can act as a Lewis base. So we create this Lewis acid base complex here, and that takes the aluminum chloride out of the reaction. Okay, so in this case, we use excess aluminum chloride, and that allows us to have half part of the material bound as the new acid base complex, and part of it to be used to create the acylium ion to make the reaction progress. Okay, now this is why we always quench with water, because we have to break up this complex here, and then we end up generating aluminum hydroxide and a whole bunch of HCl at the end of the product, okay? So the other difference between the alkylation, the Friedel-Crafts alkylation, and the Friedel-Crafts acylation is once you put that carbonyl on there, it is now less reactive than it used to be. So it's very easy to put just one group on there. So you have much better specificity about which carbon is bonded to it and how many you put on there with the Friedel-Crafts acylation, okay? Questions on that? Okay, I want to go through one more slide and then we'll take a break. Okay, so what you'll notice is when we start doing multi-step synthesis, we sometimes have to make our acid halides or our acid anhydrides. And where'd that go? There we go. So in the case of carboxylic acids, we'll actually be doing a whole bunch of this in chapter 17. However, it helps us to do these, to remember what these are. We can use some of the same reagents we use to make alkyl halides, the thionyl chloride, or we can use this phosphorus pentachloride as well. And that'll convert any carboxylic acid into an acid chloride, okay? And that acid chloride is that reactive species we use for this Friedel-Crafts acylation. The other thing we can use is we can use that acid anhydride. And to generate an acid anhydride, we can typically use an acid chloride and either a carboxylic acid or a carboxylic acid salt. And again, we'll go over this again in chapter 17, so don't worry about it. This is just where we generate these species. Okay. So now let's do a compare and contrast of alkylations and acylations. Okay. So powerful electron withdrawing groups makes the ring less reactive to acylations or alkylations, okay? Meaning if you have any of these electron withdrawing groups, and think of electron withdrawing groups as anything with a partially positive carbon on it or a positive carbon on it, they do not react. So this has a partially positive nitrogen here, this has a positive nitrogen, this has a carbonyl, which is partially positive carbon. All of these are pulling electron density away from the ring. When you pull electron density away from the ring, it makes the reaction give poor yields. Now, the reason that aniline here is that aniline is a Lewis base and will immediately react with your Lewis acid and generate a charged species here. Now we have a charged species that acts, that's electropositive here, and that pulls electron density out of the ring, okay? So in the case of anything with these electron withdrawing groups or aniline, they tend to be non-reactive or poorly reactive to the Friedel-Crafts reaction. Okay, so I'm going to stop here and then we're going to move on after the break. Okay, so any questions right now talking about the different reactions we have on benzene? Am I not hearing people? Hello? Okay, so what I'm going to do is I'm going to go ahead and stop recording and then hang out for about 5 minutes and then go ahead and